exercises use Newton's law of cooling, which involves a function uppercase T of T, which is the temperature of an object T time units after being placed in a new surrounding. Initially, lowercase t would be 0. It stands for the time. Uppercase T of 0 will be the initial temperature of the object when it is placed in the new surroundings. And capital T sub S is the temperature of the surroundings. Notice that the capital T in capital T sub S is independent of the capital T function, which deals with the temperature of the object. Notice also that we could define another constant by looking at the difference of T sub 0 and T sub S. This is the initial difference in temperature between the object and its surroundings and is labeled D sub 0. We note that as lowercase t approaches infinity, that is, as the object is left in its new surroundings, the temperature of the object approaches the temperature of its surroundings. The formula that provides this is capital T of T equals T sub S plus D sub 0 e to the minus kt, where k is a constant. And that constant k depends on the makeup of the object. So looking at the first application, we see that we're dealing with forensics here. And the fact that the body temperature of a person at the time of death is 98.6 degrees Fahrenheit. That's our T of 0. And also that for the human body, the K has been computed to be 0.1947. And in this situation, we're talking about the body in a room at 50 degrees Fahrenheit. So T sub S is 50 degrees. So the function that models this situation, the temperature of the body, would be capital T of T equals T sub 0, T sub S, the temperature of the surroundings, which is 50 degrees, plus the D sub 0. And D sub 0 in this application is 98.6 minus 50, or 48.6 degrees Fahrenheit. And so T of T is going to be 50 plus 48.6 times e to the minus 0.1947 t. So that is our function in this case. Now, part B says if the temperature of the body is 75 degrees, how long ago was the time of death? So now this is actually the value of T of T. So 75 would equal 50 plus 48.6 e to the minus 0.1947 t. And we're looking for the lowercase t. First of all, we'll subtract 25 from both sides and divide by 48.6. We're subtracting 50 and dividing by 48.6 to get 25 divided by 48.6 equals e to the negative 0.1947t. By taking the natural log of both sides, we will get a value for the exponent. And I'm going to use the quotient rule for logs, which says that the log of the quotient is the difference of the logs. So natural log of 25 minus natural log of 48.6 is going to equal natural log of e to the power, and because the natural logs and exponential with the same base are inverses of each other, we're left with the exponent. Now we're going to divide both sides by negative 0.1947, and that gives us the exact value for t. Now we will get the approximate value for t by, by keying in, first of all, an open parentheses, natural log of 25, close the parentheses for the log, subtract natural log of 48.6, close the parentheses for that log, close the parentheses for the numerator, divide by negative 0.1947. And when we hit enter, we get 3.414 hours. It says to round to the nearest whole number, so we'll call that 3 hours. So the body has been dead for 3 hours. In our next example, we're dealing with a turkey that is being taken out of the oven. And the turkey, when it is done and taken out of the oven, is 185 degrees, has a temperature of 185 degrees Fahrenheit, and it's being put into a room 51 degrees Fahrenheit. So notice that for this situation, D sub 0 is equal to 185 minus 51, which will be 134 degrees Fahrenheit. And so our formula would be in the form capital T of T equals 51 plus 134 e to the minus kt. Now we're not told either k or t yet, but in part A we are told that the temperature of the turkey is 150 degrees Fahrenheit after half an hour, and asked to find the temperature after 45 minutes. And so we are asked if T of 0.5 equals 150 to find T of 0.75. So first of all, knowing that T of 0.5 is 150, we can replace the T of T with 150. So we get 51 plus 134 e to the minus k times t, which in that case then is 0.5. So being given this gives us the ability to find the value of k and then use that to find the temperature after 3/4 of an hour. And so we're going to subtract 51 from both sides. That'll give us 99. We'll divide by 134. And that is going to give us e to the negative 0.5k. Taking the log of both sides will be the natural log of 99 minus the natural log of 134 will equal negative 0.5k. We divide by the negative 0.5 to find our k. So using the calculator, we're going to be able to find our k. So it's going to be it should be 99. I had written 90 here. So 99. And so going back to the calculator, we'll have left parentheses, natural log 99 minus natural log 134. And I have forgotten to close the parentheses on the 99, so I'm going to back up and do that. Minus natural log of 134, close the parentheses on the 134, and then close the parentheses on the numerator, divide by negative 0.5. Enter. And we get k is equal to 0.6054, etc. We'll just keep one decimal place for that k and call it 0.6. And so now we can use that k to find t of 0.75. It will equal 51 plus 134 e to the minus 0.6 times 3/4 or 0.75. I'm going to do 3/4 here. T is 3/4 or 0.75. And so we can use the calculator here and enter 51 plus 134 second natural log parentheses. I'm sorry, those parentheses are already there. I'm going to go back and take that parentheses out, and it will be negative 0.6 times 0.75. Close the parentheses, hit enter. And so the temperature to the nearest whole number would be 136 degrees Fahrenheit would be the temperature. So it started at 185. After half an hour, it was 150. After 45 minutes, it's 136 degrees. Now, the last part of the problem asks us to find out when the turkey will cool to 100 degrees. So we would set up the equation 100 equals 51 plus 134 e to the minus 0.6 t. I'll put the answer in the comments to this video. Try it yourself.